In part 1 of this video, you learned what a proportion z-test is and the various steps you need in order to perform that hypothesis test. For example, we started with some assumptions. As you see here, we reviewed a little bit how to determine the null and alternative hypothesis, the importance of the level of significance, and how to use this formula here to compute the test statistic. These steps will not change in any proportion z-test that you run. In order to better understand these steps and the ones coming up, we used the aspirin example as a way to do so. So just starting now, part 2, let me read this example again. It says a medical publication claims that 90% of doctors recommend aspirin for their patients with headaches. The CEO at a local hospital believes that this claim is too high. To test the claim, a random sample of 200 doctors is obtained, and 172 indicate they recommend aspirin at the 5% level of significance. Do the data provide evidence include the CEO is correct? Okay, so just remember that p sub 0, 0.90. P hat was 172 over 200, which ended up being 0.86. And of course, our n in this problem is our 200, and alpha is here, 5%. So we used the problem and all of this information in order to formulate our null and alternative hypothesis. We were stating that this is a left-tailed test. Remember, the CEO thought it was too high, which means he expects it to be less. Level of significance is alpha is 0.05. And then here I just showed you how we calculated the test statistic in order to get negative 1.89. At this point, we moved on to our step 4 and used a critical value method in order to formulate a decision on whether to reject or fail to reject the null hypothesis. While the critical value approach or method is a very valuable tool in the world of statistics, especially for students to understand the concept of rejection regions and so forth, it is actually the least popular method. You don't see a whole lot of statisticians looking for critical values. Instead, the p-value approach is the primary method for decision making. This p-value method utilizes area as a way to make a decision in a hypothesis test rather than some value of z, like a critical value. Just like we did last time, what I want to do, since we are going to do an example of all of these, is I want to focus strictly on the type of test that we're doing and then worry about the other ones when we have an example of it. So as you recall, this is a left-tailed test because it's a less than test. And according to our image here, the p-value is going to always be equal to the probability that z is less than the value of our test statistic. So what does that mean for us? That means that the p-value in this problem is going to be equal to the probability that z is less than, as stated, our z sub 0. Now, this is our z sub 0 right here, negative 1.89. Now, I claim that you know how to do that already. What is this asking for? Well, you're basically looking at whatever our curve is, right? Remember our standard normal curve that we were normally write with 0 in the middle. We're looking at negative 1.89, which is our test statistic. And we're finding the area below it in the standard normal table. So just so you realize here, when we use the p-value approach, we're no longer taking our value of z and sticking it in our back pocket and saving it for later. going on to work on rejection regions and so forth, and then bringing it back into play. When we do the p-value method, we immediately take our test statistic, throw it on the graph, and determine the proper area that the p-value requires. So, of course, we can go into our z-table, if you recall. So our z-table, what we're looking up is negative 1.89. So negative 1.89 is going to throw us at 0.0294. So we move back. This is 0.0294, which means the p-value is 0.0294. So why exactly is this valuable to us? Well, we still haven't made a decision yet. That's where this comes in, right over here. It says, if the p-value is less than or equal to the specified significance level, reject the null hypothesis. Otherwise, do not reject the null hypothesis. So in other words, if our p-value is less than or equal to alpha, we reject H naught. Okay, so let's look at our decision here. So is our p-value, which is 0.0294, less than or equal to our alpha? Well, remember our alpha in this problem was 0.05. So that's where that level of significance comes in. So is that true? Yes, that is definitely less than 0.04. Therefore, what do we do based on what this is saying? We reject H naught. And if you recall, we rejected H naught in the previous example as well, using the critical value method, which is what you would expect. It's the same problem and the same scenario of values for the variables. So therefore, again, we reject H naught because the p-value is less than or equal to our alpha. One thing to take note of here is that this rule of p-value less than alpha is standard no matter what type of test you're running. So even if it's in the right tail or both tails, whatever it is, we always use less than or equal to. But there's a reason for that, which I want to detail here as well. What I did was I brought back over here, so we're recalling here, our critical value approach that we used. This is not here to confuse you or anything. It's just meant so that you understand that the p-value method is not me rewriting the book, so to speak, on how to do this. It's actually just a replacement, an area replacement for the z-value that we used for our critical value. What do I mean by that? Well, when we found the critical value for this test in the previous video, it was negative z sub alpha or negative z sub 0.05. This resulted in a critical value of negative 1.645. Now, one thing that's worth mentioning is that also means that this right here is an area of 0.0500. So because we're looking for a z value with an area of 0.05 that would be above it in the right part of the tail, if we put a negative in front of it, that means it's going to be the area in the bottom part of or below negative 1.645. So if you look at that really carefully, if we end up with, and remember this is alpha right here, right? If we end up with any other area that is lower than that, what does that actually do for us? Well, if we end up with an area of, let's say, just like our problem up here, let me move up a little bit, 0.0294, that means that the value that you're going to get is actually going to go farther down here. So let's say this is 0.0294. So if this area is less than alpha, that means the value of z is also going to be less, which ends up being negative 1.89. So really what's happening here is instead of me saying, oh, negative 1.89 is less than negative 1.645, So we're in our rejection region and reject H naught. Instead, we're taking the area to the left of it and saying it's less than the area to the left of this, which is again going to pull the value out into the tail into the rejection region. This is just, yes, this is a little complicated and weird sounding, but that is the logic that's going on here. Is all we're doing is using area as a replacement for the critical value in making our decision. So instead of saying, hey, our critical value negative 1.645 is the cutoff, now we're saying our area value 0.05 is the cutoff. That is a good way to think about it, and hopefully that helps you understand that the methods are kind of in sync, but it's just a different approach to this. And again, both approaches need to be studied and known because you will be applying both. And the p-value is the most popular one that is used in the workplace for statisticians. So before I forget, I just want to make sure that you understand that the interpret step is also going to be required no matter what decision-making method you use, critical or p-value. So it's going to be identical. There's no change. So in this problem, we would say literally the same statement in the previous video example where we use the critical value method. At the 5% level of significance, the data does provide, because we reject H naught here, sufficient evidence to conclude that the doctors prescribe aspirin for headaches less than 90% of the time. Always remember to interpret at the end of your hypothesis test. Before we move on to the rest of the examples, one thing you want to take forward with you is that low p-values will always lead to rejecting H naught. So why exactly is that? Well, by definition of p-value, a low p-value will indicate that it is very unlikely to get the results you're getting just by random chance if the null hypothesis is true. This would then in turn give us strong evidence to side with our alternative hypothesis against our null hypothesis, which means we would end up rejecting H naught. All right, so let's move on to our next example. It says an apple farmer has in the past lost an average of 3% of his trees each year. He notices that he has been losing more trees lately. In a random sample of 200 trees, 11 have died. Is this sample evidence at the 10% significance level that his loss rate is greater than 3%, perhaps due to some environmental factor? For the purposes of the next couple examples, I won't be doing assumptions. They are satisfied, by the way, but I'd like to just get into the steps of the hypothesis test so we can crank out these examples. So first things first, by looking at this problem, you can obviously see again, we have some evidence here. We got a 10% significance level. It's screaming that it's a hypothesis test. We also have some proportions here. We have a 3%, we have 11 out of 200, so we're dealing with proportions. So we're definitely going to be dealing with a 1 proportion z-test. It looks like our p-hat is going to be 11 out of 200. That 11 out of 200 is going to be 0.055. And it looks like this guy, this 3% here, is going to be our p sub 0, 0.03. We have a alpha of 10%. Just remember that this 200 will end up being our n. So what does our null and alternative look like? Remember, the null is a statement of equality about the population proportion. So that's the 3% value for the number of trees that the apple farmer has lost. Our alternative, we are looking for hints that lead to less than or greater than, or if not, then we go to a not equal to two-tailed test. Well, you can see that it says that he's been losing more trees lately, so it looks like we're going to be doing a right-tailed test with p greater than 0.03. This problem is actually going to be at the 1% significance level. I know it said 10% a second ago, but I just forgot to change it when I copy-pasted over. This is going to be alpha equals 0.01. And for our test statistic, nothing's changed here. Just remember the formula is going to be our p hat minus our p sub 0 over the square root of p sub 0, 1 minus p sub 0 all over n. So we're going to take our 0.055, we're going to subtract our 0.03 all over. Remember, we're using p sub 0 in the rest of the problem. There are two p's here, so we don't want to confuse those. And we're going to end up with 2.07 when we round to 2 decimal places. Again, this is our test statistic. If we were running the critical value method, we would essentially just take this 2.07, stick it on our back pocket, and save it for later. We would then go on, we would find the critical value, in this case, or values if it was a not equal to test. We would set up the rejection regions in a picture, and then we would find where this 2.07 falls. That is not what we're doing anymore. We're now using the p-value method. So in the p-value method, we don't keep this in our back pocket, believe it or not. What we do is we actually draw out a graph and we place 2.07 on said graph as our value of z sub 0. We now return to our guide over here for right-tailed tests. So now we're here. Now, according to a right-tailed test, the p-value is always going to be equal to the probability that z is greater than our test statistic z sub 0. So let's write that out. So our p-value is going to be equal to the probability that z is greater than z sub 0. Now, in that case, that means we're looking for the probability that z is greater than 2.07. So this conveniently puts us in the right tail of our distribution, which makes sense because we are dealing with a right-tailed test. The p-value, therefore, is going to be whatever this area is on the right side of 2.07. Therefore, you just have to bring back some of your skills with using normal distributions and how to find area above. So, of course, you do look up 2.07 in our z table. 2.0 and then 7 is going to put us about right here, which is at 0.9808. So remember that that is going to give us the area below 2.07, which means the area above it, which is the p-value, is going to be 1 minus 0.9808, which is going to give us 0.0192. So again, you want to make sure that you have your skills down for earlier material that you've covered. So remember, area above is going to be 1 minus the area below. So this officially here is our p-value, which means we can go ahead and we can use our decision criterion in order to determine whether we reject or fail to reject H naught. So here's our decision over, actually let's put it over here since that's where the p-value is. So what do we ask ourselves? So we ask ourselves, is p less than or equal to alpha? In other words, is 0.0192 less than or equal to our 0.01? The answer to that is clearly no. So remember what happened when it was less than, we rejected H naught. So up here, what it says is, otherwise, do not reject H naught. That is the key. So therefore, we would say, therefore, do not reject H naught. Okay, I wrote some of this down already for our interpret step. We would say at the 1% significance level, remember I changed that, the data does or does not provide. Well, if we do not reject H naught, then it does not provide sufficient evidence to conclude that, and then we have to restate the alternative hypothesis in words. So you can say loss rate or tree loss rate, include that the apple tree loss rate is greater than 3%. So this is all the formality of it, of course, but just to be clear, to make sure you're understanding, is if we do not reject H naught, that means we're siding with the null hypothesis and that we don't believe that the tree rate is greater than 3% based on the sample that we have put together and our p hat. Okay, before we move on to the next example, let me just state a cautionary tale here, or in other words, a mistake that students make. So when they get down to this step right here, when they're making their decision, they kind of overthink things and they start thinking that for some reason this inequality symbol must change because of the fact that it's a right-tailed test. That is not the case. This statement here is the same no matter what for all tests that you run, left, right, or two-tailed. Why? Because again, if remember the thing I had you leave with here, low p-values always reject H naught, which means we're always looking for them to be less than or equal to alpha. All right, let's look at this next example. A recent publication stated that the rate of smoking among students after 4 years of college is 27%. A survey showed that among 785 randomly selected subjects who completed 4 years of college, 23.5% smoke. Is there sufficient evidence at the 10% significance level to conclude that the proportion differs from the publication's claim? Okay, so again, looking at this problem, we do see they're talking about sufficient evidence and that we do have a significance level. We also see that we have proportions all over the place, so this is going to be a one proportion z-test. Always try to find that p hat right off the bat. This time they did give you n here, but unlike some of the other problems that we've seen, they didn't give you the value of x, which is the number of successes. Instead, they came out and just gave you p hat. So p hat is going to be equal to 0.235. So don't overthink that. I know you're used to putting a 785 somewhere in there, but you do not do that. You just put the p hat and call it a day. That also means that this guy is going to be our population proportion, as 0.27. Alpha is sitting right here. So the assumptions do get satisfied. Let's move on to our null and alternative hypothesis. We have a statement of equality with the population parameter p, and we include p sub 0, which is 0.27. We also now are looking for any type of word that would signify left or right. You're actually not going to find that anywhere. Instead, they do even give you a bigger clue by using the word differs, which implies not equal to. So we have p is not equal to 0.27, and we have our first two-tailed test for the p-value method. Alpha is given as 0.10. We need to calculate our test statistic, which is going to be equal to 0.235 minus 0.27 over the square root of 0.27 times 1 minus 0.27. Again, don't get confused by these or flip them or anything like that. Put the wrong number below. Make sure you're very clear with which one you're using along the way there. We're going to divide by 785, which is a nice healthy sample. If we do so, we're going to get negative 2.21 as our test statistic. Okay, so remember that now we're going to take this test statistic and we are going to place it on our graph, but we need a little bit of guidance before we start doing anything here, because remember above we have a little printout here that shows us what to do whenever we're dealing with two-tailed tests. Okay, you can clearly see that we're supposed to put our value of z sub 0 somewhere on the graph, but then we need to put the opposite value on the other side of the graph to create two tails. So let's do that first. So we got negative 2.21, which is going to have an area to the left, which means we also have to have its symmetric buddy, positive 2.21, on the right side, which means we're going to shade on the other side of 2.21. Moving on to back to our graphic here. So it looks like that the p-value is going to be equal to 2 times the probability that z is greater than the absolute value of z naught. So that's a lot going on there. So we want to write that down here and make sure that that's fully explained. So the p-value is going to be equal to 2 times the probability that z is greater than the absolute value of z sub 0. There are a couple ways to do this, but by definition, what is it saying to do? Well, we know z sub 0 here is our test statistic, so we would plop it in there, right? But then we would take the absolute value and make it positive. So what it's saying is take the probability that z is greater than positive 2.21, which would be this. Once you find that, then according to this, you multiply it by 2, which really is the equivalent of just taking both of these, because these are symmetric to one another. So taking one of them and multiplying by 2 is giving us the full area in both tails. But the reality is we don't have to really go by the pure definition of it here. We can literally just find the area in either one of the tails and multiply by 2. So it's usually easier to find the area in the bottom tail because that only requires that you look up this number. If we look up this value over here, we have to subtract it from 1 to get the area in the upper tail. So it seems like it's much easier to do the lower one. So let's do that now. So we're going to look up negative 2.21, which is going to give us this value right here, which is going to be 0.0136. So this right here is 0.0136. So we're looking for 2 times that, which is going to give us 0.0272. And that is going to be our p-value. So again, when you get your test statistic, you place it on your graph, you put the symmetric opposite version of that on the other side. You make your 2 tail shaded areas. You find the area of one of them and you multiply by 2 to accommodate the fact that it could be less than or greater than. That's what we're doing here. We have a not equal to test. So therefore, we need to take into account it could be less than or greater than, and that's how the p-value handles it in these types of problems. Okay, moving to our decision step, we would say, is our p-value less than or equal to alpha? So in other words, is 0.0272, so yes, the p-value is the value after it is doubled, less than or equal to our alpha, which is right here, 0.10. Clearly, we look at that and see that it is less, so we would say yes, therefore, we would reject H naught. This would, of course, lead us to side with the alternative because we're rejecting that as fact. So basically, we think that the proportion differs from the publication's claim based on the sample. For our interpretation, we would say at the 10% significance level, the data, well, what did we do? We rejected H naught, so the data does provide sufficient evidence, and then we would just restate our alternative hypothesis that the proportion of student smokers differs, or you could say is not, but since they use the word differs in the problem, we'll go with it, differs from 27%. So we've been through a bunch of problems here that have basically shown you how to complete and pull off using the p-value approach to decision making, which is right here. Just make sure that you are very clear on how to do this. None of the methods involved with the critical value or p-value approach are in the formula sheet, which means this is something that you will have to study and know very well. So be ready for any of this on exam problems.